Hello students, welcome to my YouTube channel once again. And here in previous video we have studied standard 12th physics unit 8 section 8 to 1, that is determination of a specific charge of an electron, that is E by m value by Thomson's experiment. Here we will study from section 8.2.2 today, but let me give you one more hint that if you have new book of year 2021, then this lesson is the ninth unit. Okay, so whatever things given here, it will be given as section 922, 933, something like that. So here today we will start from determination of charge of an electron by Millikan's oil drop experiment. You know very well that what is the what is the charge on an electron, proton and neutron is chargeless. Okay, how have we determined it? How Millikan has done to find out how much charge an electron has? So let us see first the setup as given here. So this figure gives you the original setup. Okay, so as given here, this is the original setup. Okay, and this is the thing which is staying inside this setup, as you can see in this figure. Okay, and here this is the model figure. Okay, as you can see. So let us start section 822 from old book and section 922 from the new book. Millikan's oil drop experiment is another important experiment in modern physics which is used to determine one of the fundamental constants of nature known as the charge of an electron. So here we try to find out how much charge an electron has. Okay, and this is the correct value till now. Whatever value we are following for the charge, okay, it is given to us by Millikan. Okay, it may be possible that further some of you will do some experiment and will find out that whatever the value Millikan has given, it is slightly different, then your value will be considered and you will get a Nobel Prize for that. Fine, so let us start this with the experiment or with the setup. By adjusting electric field suitably, the motion of oil drop inside the chamber can be controlled. We know very well that whenever any object falls from top to bottom, okay, without any net force acting on it, in that situation the gravitational force acts on that in downward direction, and the object or the point or anything which falls down comes with a gravitational acceleration, that is 9.8 meter per second square. If suppose there happens some suitable arrangement by which we can make this object to fall down with a constant velocity, or it may be possible, is it possible that the object is falling down and by some suitable arrangements we make the object to hover over the ground? It is done by Millikan. What happened here is the oil drop is dropped from a height, certain height, okay, simply dropped downward, and when it was falling with gravitational acceleration g at 9.8 meter per second square, okay, with the help of some external arrangement by giving some external electric field, it is made in such a way that the drop of the oil, which is very small, okay, is made to hover over the ground or started floating over the ground for some time. That is, it can be made to move up or down or even kept balanced in the field of view for sufficient long time. Okay, that means that the force downward, that is mg, and the force upward, okay, because of the electric field is balancing each other. Once again, if suppose an object is there and if on the object net force is 0, then the object will move with constant velocity or will move at rest. If suppose the force by which the earth attracts anything in downward direction, that is mg, okay, if same amount of force is acting on the object in upward direction, in that situation net force will be 0 and the object will hover at one point or will fall down or go up with some constant velocity. Okay, these two parallel plates, let me see once again what are things given here. Okay, and the experimental arrangement is shown in figure 8.6b. as you can see here, this is the experimental setup, and this is given in figure 9.6 in the new book of year 2021. The apparatus consists of two horizontal circular metal plates A and B each with diameter around 20 centimeter and are separated by a small distance of 1.5 centimeters. So here you can see that this is actually circular in shape, okay, and here plate A is circular, just like circular lamina, and plate B is also circular, whose diameter is just 20 centimeter and the gap between plate A and plate B is just 1.5 centimeter. As you can see here, a microscope is attached in between A and B, so that when the oil drop will come through the atomizer and will fall down, the microscope can see its movement, capture its movement. Okay, fine. These two parallel plates are enclosed in a chamber with glass walls so that we can see it from outside. Further, plates A and B are given a very high potential difference of the order 10 to 10 into 10 to the power 3 volts, that is 10 kilovolts, such that electric field acts vertically downward. Okay, so as you can see here, the electric field is acting vertically downward. Why it is taken downward, we will see here. A small hole is made at the center of upper plate A and atomizer is kept exactly above the hole to spray the liquid. As you can see here, at the center of this cylinder, a small hole is made in such a way that when the liquid drops or oil drops will come out of it, it will get atomized, means very small droplets, and it will fall down. Okay, fine. When a fine droplet of highly viscous liquid, suppose like for example glycerine, is sprayed using atomizer, it falls freely downward through the hole of the top plate only under influence of gravity. That means if suppose the glycerine particles comes out of the atomizer, okay, here the atomizer is not forcing the glycerine particles, it is just falling down by acceleration due to gravity or gravitational force. It will fall down with the influence of gravity. Few oil drops in the chamber can acquire electric charge because of friction with air or passage of X-rays in between the parallel plates. Earlier, when we have studied about X-rays in the previous chapter, we have studied that whenever X-ray falls on any object or any gas, okay, it knocks out the electron from the surface and makes the object or the gas, okay, electrically charged. So what happens here is, when these droplets of glycerine will fall down, it will acquire some electric charge because of bombardment of X-rays, okay, or because of the air friction. Further, the chamber is illuminated by light which is passed horizontally, and oil drops can be seen clearly using microscope placed perpendicular to the light beam. As you can see here, a light source is given in such a way that we can see that atoms or the liquid oil drops coming out or the glycerine drops coming out from the atomizer. These drops can move either upward or downward. Here it will move upward or downward because of a net force acting here, and this net force is zero. Okay, why this net force happens there zero, let us see, as given in figure 8.7a and b. Fine. Let m be the mass of the oil drop and q be its charge. Every object has charge except that of neutron. Then the forces acting on droplets are, we will have gravitational force mg acting downward, electric force QE, okay, so as you can see here, Fg downward acting, okay, then Fe electric force, then buoyancy force Fb. Here buoyancy force will be because of the air droplets or air particles filled inside this plate A and B. It will work vertically upward, and then viscous force Fb, that will also work in vertically upward direction. So as you can see here, the forces acting on the oil drop are Fg downward. Here you can see two figures A and B. In first figure, when the oil drop was falling down and no electric field was applied, then we have the forces acting like Fg downward, Fb buoyancy upward, and we will have viscous force upward direction. But when we have electric field acting in between the plates A and B, then the forces acting on the particles are Fg downward, that is force because of gravity, okay, then buoyancy force upward and electric force in upward direction. Okay, now let us determine how to find out the radius of the droplet. Determination of radius of the droplet means the glycerin drop which is falling down, what is its radius? When the electric field is switched off, the IL drop accelerates downward, that is because of gravity. Due to the presence of air drag forces, the IL drops easily attain its terminal velocity and moves with constant velocity. What happens here is because the IL drop is very small, that viscous IL drop is very small, okay, and when it will fall down, it will have to overcome very high viscous force because of the air, and because of that the IL drop will get a terminal velocity, after which the upward and downward force will become equal, and then the IL drop will fall down with a constant velocity. This velocity can be carefully measured by noting down the time taken by the IL drop to fall through a predetermined distance. Okay, as given here, the distance between plates A and plate B is just 1.5 centimeters. Alright. The free body diagram of the IL drop is shown in figure 8.7a. We know that viscous force and buoyant force, they balance the gravitational force. Means if suppose the IL drop is falling downward with constant velocity, that means Fg will be equal to Fb plus Fv. Okay, in case when electric field was absent and when electric field was applied, then we will have Fg is equal to Fb plus Fe. Alright. Let the gravitational force acting on the IL drop in downward direction is mg. Okay, let us assume that IL drop to be spherical in shape. Okay, we know very well that because of surface tension, the liquid drops, if it is falling down, will always have a perfectly spherical shape. Let rho be the density of IL drop and r be the radius of IL drop, then the mass of IL drop can be expressed in terms of its density, that is rho is equal to, density is equal to mass by volume. We know it very well. Okay, all right, so we will have mass is equal to density into volume, okay, as given here, and we know very well that the IL drop is perfectly spherical in shape in that situation. If suppose if the radius of the IL drop is r, then the volume will become 4 by 3 pi r cube, that is the volume of a sphere. The gravitational force can be written in terms of density as Fg is equal to mg, okay, or Fg is equal to, at the place of m, we can write this one, rho into 4 by 3 pi r cube. So Fg, gravitational force, is equal to rho into 4 by 3 pi r cube into g. Let sigma be the density of air which is trapped between the plates A and B, okay, and it gives the upthrust. Okay, the upthrust force experienced by the IL drop due to displaced air is given by Fb is equal to sigma into 4 by 3 pi r cube into g. Okay, so here the amount of upthrust will be equal to the amount, see, the amount of air displaced will be equal to the amount of IL drop. Okay, so the volume of IL drop we have 4 by 3 pi r cube. Okay, then the upward force because of the air drag will be given by sigma into 4 by 3 pi r cube into g. Once the IL drop attains the terminal velocity, it means that the downward force and upward force will become equal. Okay, the net downward force acting on the IL drop is equal to the viscous force acting opposite to the direction of motion of the IL drop. From Stokes' law, the viscous force on the IL drop is given by Fb is equal to 6 pi r nu eta. Okay, this is given in the second volume of standard 11 physics. Okay, buoyancy force is equal to 6 pi r nu into eta. Okay, now from the free body diagram, as we have seen earlier, okay, the balancing force is equal to Fg is equal to Fb plus Fv. Okay, as given here, Fg is equal to Fb plus Fv in case when electric field is 0. All right, so we can just substitute the values. We will have rho into 4 by 3 pi r q g is equal to sigma into 4 by 3 pi r q into g plus 6 pi r nu eta. Okay, so here let us just rearrange it, and by that we get r is equal to the square root of n eta nu by 2 into rho minus sigma into g. Okay, so this gives the radius of IL drop. Now determination of electric charge. How to find? By this figure, by equation 8.11, we can find out what is the radius on radius of the IL drop or the glycerin which is coming out of the atomizer. Now let us discuss about the how we can determine the electric charge. Alright, so let us find what is given here. When the electric field is switched on, charged IL drop experience an upward electric field force, that is Q into E. So here in this equation 8.11, we have tried to solve this equation with the help when we have no electric field working in this figure. Okay, in this situation when electric field is switched off, and now we will see all the other things. Among many drops, one particular drop can be chosen in the field of view of microscope, and the strength of the electric field is adjusted to make that particular drop to be stationary. So what happens here is, let us see the figure once again. When from the atomizer the glycerin particles are falling down, or any other viscous viscous liquid is falling down, okay, we adjust the electric field in such a way that a particular drop is made to move with the determined velocity. Okay, whether that particle will stay at some one instant, okay, for a long time, or whether it will move vertically upward or downward with a constant velocity. That means net force acting there in upward and downward is equal to 0. Under these circumstances, there will be no viscous force acting on the IL drop. Okay, then from the free body diagram shown in figure 8.7b, the net force acting on the IL drop, as we can see once again from this figure 8.7b, or in your book from 9.7b, that Fg is equal to Fb plus Fe. Okay, so here this is the situation when the electric field is working in between the plates, okay, and on the IL drop. So just substitute the values. We will have Fe plus Fb is equal to Fg. That means total force in upward Fe plus Fb is equal to total force in downward direction, that is Fg. Okay, and now substitute the value. Total electric force is given by Q into E plus Wan's force 4 by 3 pi r q rho into g is equal to rotational force 4 by 3 pi r q into rho g. So we will have QE is equal to 4 by 3 pi r q into rho minus sigma into g, or Q is equal to 4 by 3e into pi r q into rho minus sigma into g. Substituting all the values in equation 8.12, from equation 8.11 in equation 1.12, we will get Q is equal to 18 pi by e into root eta q nu q by 2 into rho minus sigma into g. Substitute all these values, we will get the value of charge on an electron. Okay, Millikan repeated this experiment several times and computed the charges on IL drops, and every time he got the same value. He found that the charge on any IL drop can be written as integral multiple of a basic value, that is minus 1.6 into 10 to the power minus 19 coulomb, which is nothing but the charge of an electron.